Voyager 1, the last signal. Somewhere, more than 15 billion miles from the bed you are lying in right now, a small machine is sending a signal. It is the faintest whisper you can imagine, 20 billion times weaker than the power of a watch battery by the time it reaches Earth. It has been traveling at the speed of light for more than 22 hours just to get here. And when it arrives, a giant antenna in the California desert, or in the red soil of Australia, or on the plains of Spain, catches it, amplifies it, and turns it into numbers on a screen. Data, science, a message from the most distant human-made object in existence. This is Voyager 1. It was launched on September 5th, 1977. It was supposed to last 5 years. It has lasted nearly 50. And its signal, that thin thread of radio waves connecting us to the edge of everything we know, is fading. The power source that keeps Voyager 1 alive is slowly dying. Every year, it loses a little more energy. Every year, another instrument is shut down to conserve what remains. And one day, perhaps within the next decade, the last instrument will go dark, the last signal will be sent, and Voyager 1 will fall silent forever. But not yet. Tonight, the signal is still there. Faint, steady, faithful. And what it carries back to us, from a place no human will visit for thousands of years, is a story unlike any other. A story of storms and rings and volcanoes and frozen geysers. A story of a wall of fire at the edge of our solar system and a gentle hum in the space between the stars. A story of the farthest journey ever taken and the longest goodbye ever spoken. Tonight, we follow that signal. From the launch pad to the stars, this is the story of Voyager 1. Before we continue our journey into the void, please take a moment to like this video and subscribe to Cosmic Drift. It helps our community of sleepy explorers grow and ensures you never miss a voyage. To understand what Voyager 1 found out there, we need to talk about where it is. There is a word that scientists use when they talk about the edge of the solar system. That word is heliopause. It sounds gentle, almost musical, but what it describes is something enormous. The heliopause is the place where the wind from our sun, a constant stream of charged particles that flows outward in every direction, finally runs out of strength. Beyond that line, the sun's influence fades, and the cold material drifting between the stars takes over. For most of human history, we did not know where this boundary was. We did not know what it looked like, or what it felt like to cross it. We only knew that it had to exist somewhere out there far beyond the planets, far beyond anything our telescopes could show us. The concept of the heliosphere and its boundaries was first proposed in the 1960s by scientists who studied the solar wind. They realized that the stream of particles flowing from the sun must eventually run into the material between the stars, and that somewhere, far from the sun, the two would meet. But predicting where this would happen was extraordinarily difficult. Estimates of the distance to the heliopause range from about 50 astronomical units to more than 200. The only way to find out was to go there, and then the Voyagers reached it. Voyager 1 crossed the heliopause on August 25, 2012. Voyager 2 followed on November 5, 2018, and what they found there changed the way we understand our place in the galaxy. But to really appreciate what Voyager 1 discovered at the edge, we need to go back to the beginning. Back to a time when the idea of sending a machine to the outer planets seemed like a dream. Back to the summer of 1977, when a golden spacecraft sat on top of its rocket in Florida, waiting to begin the longest journey in human history. The story of the Voyager missions starts not with the spacecraft themselves, but with the planets. In the late 1960s, an aerospace engineer named Gary Flandreau was working at the Jet Propulsion Laboratory in California. He was studying the orbits of the outer planets, Jupiter, Saturn, Uranus, and Neptune, and he noticed something remarkable. Once every 175 years, these four giant worlds line up in a way that allows a single spacecraft to visit all of them, one after the other, using the gravity of each planet to sling it toward the next. This rare alignment was going to happen in the late 1970s, and it would not come again until the 2150s. The technique that makes this possible is called a gravity assist. When a spacecraft flies close to a planet, it can use the planet's gravity to change its speed and direction, accelerating without burning any fuel. The energy comes from the planet itself, which loses an infinitesimally tiny amount of its orbital energy in the exchange. Without gravity assists, a mission to Neptune would take about 30 years. With the alignment that Flandreau discovered, the trip could be done in about 12 years. Flandreau knew that if NASA could launch a spacecraft at the right time, it could ride the gravity of these planets like a surfer catching a wave. The trip would take about 12 years instead of 30. It was a once-in-a-lifetime opportunity. Actually, it was a once-in-several-lifetimes opportunity, and NASA decided to take it. The original plan was called the Grand Tour. It was ambitious, bold, and expensive. Too expensive, it turned out. Congress cut the budget in 1972, redirecting funds toward the Space Shuttle program, and the Grand Tour was scaled back to a simpler mission. The original Grand Tour had envisioned multiple pairs of spacecraft visiting all 5 outer planets, including Pluto, with redundant systems designed to survive the full decade-long journey. The scaled-back version was more modest, but still revolutionary. 2 spacecraft would be sent to Jupiter and Saturn. If they survived, and if the first spacecraft successfully completed its close flyby of Saturn's moon Titan, the second might be sent on to Uranus and Neptune. The mission was initially called Mariner Jupiter-Saturn, named after the earlier Mariner probes that had explored the inner solar system. But as the design of the new spacecraft grew more complex and more capable, clearly evolving beyond the Mariner family, the team decided it deserved a new name. In 1977, just months before launch, the mission was renamed Voyager. The name was chosen after NASA held a public competition, seeking something more evocative than the technical designation. Voyager captured the spirit of the mission perfectly. These were not just probes or instruments. They were travelers, setting out on a voyage from which they would never return. And so, on August 20th, 1977, Voyager 2 lifted off from Cape Canaveral in Florida, riding a Titan rocket into the sky. 2 weeks later, on September 5th, Voyager 1 followed. Even though Voyager 2 launched first, Voyager 1 was placed on a faster, shorter path. It would reach Jupiter and Saturn before its twin. The naming was a source of some confusion. Why was Voyager 2 launched before Voyager 1? The answer was simply that the spacecraft launched second was given the name Voyager 1 because it would arrive at its targets first. It was a matter of trajectory, not priority. Voyager 1's launch was not without drama. The Titan rocket's second stage shut down prematurely, leaving more than 1,000 pounds of propellant unburned. The spacecraft was in danger of falling short of the trajectory it needed to reach Jupiter. But the Centaur upper stage, equipped with its own guidance computers, recognized the problem and automatically extended its burn to compensate. It was a close call, the kind of moment that makes mission controllers age rapidly, but it worked. Voyager 1 was on its way. Just 13 days after launch, Voyager 1 scored the first of its many firsts. From a distance of 7.25 million miles, it turned its camera back toward Earth and took the first ever photograph of the Earth and Moon together in a single frame. The image was simple, two small crescents hanging in the darkness, but it was a preview of the perspective-shifting photographs that would follow. It was also a reminder that the spacecraft was already moving away from home at tremendous speed. The two spacecraft were identical in design. Each one was about the size of a small car. Each carried 11 scientific instruments, including cameras, spectrometers, magnetometers, and plasma detectors. The two spacecraft were identical in design. Each one was about the size of a small car. Each carried 11 scientific instruments, including cameras, spectrometers, magnetometers, and plasma detectors. The cameras were slow-scan television cameras that could take extraordinarily detailed photographs, but they required time to build up an image line by line. The spectrometers could analyze the light coming from planets and moons, breaking it into its component wavelengths to reveal the chemical composition of atmospheres and surfaces. The magnetometers measured the strength and direction of magnetic fields, which carry information about the internal structure of planets and the nature of the space between them. The plasma detectors measured the charged particles of the solar wind and eventually of the interstellar medium. Each spacecraft was also equipped with a radioisotope thermoelectric generator, a power source that converts the heat from decaying plutonium-238 into electricity. Unlike solar panels, which become useless beyond the orbit of Jupiter because the sunlight is too faint, the RTGs work regardless of distance from the Sun. They are the only practical power source for missions to the outer solar system, and they are what has allowed the Voyagers to operate for nearly 5 decades. The spacecraft communicated with Earth through a high-gain antenna, a large dish 3.7 meters across that had to be pointed precisely at Earth to send and receive signals. At Jupiter, the data rate was about 115,000 bits per second, enough to transmit photographs relatively quickly. By Saturn, the data rate had been halved, and as the spacecraft moved farther from Earth, the data rate continued to drop, following the inverse square law until today, when the Voyagers transmit at just 160 bits per second. The signals are received by the Deep Space Network, a system of giant antennas located in California, Spain, and Australia, spaced around the world so that at least one antenna is always in view of the sky where the Voyagers are. And each one carried something else, something that had nothing to do with science. Bolted to the side of each Voyager was a golden record, a phonograph record 12 inches across, made of gold-plated copper. On it were encoded the sounds and images of Earth, greetings in 55 languages, music from every corner of the world, the sound of wind and rain and whales singing in the ocean, photographs of people, of landscapes, of our cities and our children. It was a message in a bottle tossed into the cosmic ocean, just in case someone out there might find it one day. We will return to the golden record later. But first, the Voyagers had work to do. The journey from Earth to Jupiter took about 18 months. During that time, the two spacecraft crossed the asteroid belt, that wide band of rocky debris between Mars and Jupiter. Scientists had worried that the belt might be dangerous, that the probes could be damaged by collisions with rocks. Science fiction movies had encouraged the idea that asteroid belts are dense, chaotic places, full of tumbling boulders that a spacecraft would have to dodge and weave through. But the reality is very different. The asteroid belt is mostly empty space. The average distance between asteroids is about 1 million miles. The Pioneer 10 and Pioneer 11 spacecraft had already crossed the belt without incident, reassuring mission planners that the Voyagers would be safe. And they were. The Voyagers passed through without a scratch. During the cruise to Jupiter, the spacecraft were not idle. Their instruments were calibrated and tested. The mission team practiced the complex sequences of commands that would be needed during the planetary encounters. The spacecraft measured the solar wind and the interplanetary magnetic field, building a baseline of data that would later be compared with measurements made at the outer planets and beyond. And the cameras took their first test images, demonstrating that the optical systems were working perfectly. And then, in early 1979, Voyager 1 began to see Jupiter. At first, the giant planet was just a bright dot in the camera's view. But as the weeks passed and the spacecraft drew closer, Jupiter grew into something astonishing. A world so large that more than 1,000 Earths could fit inside it. A world wrapped in bands of swirling clouds, painted in shades of orange, white, cream, and brown. And there, in the southern hemisphere, was the Great Red Spot, a storm larger than Earth itself, a storm that had been raging for centuries, maybe longer. The Voyager cameras showed it in detail that no telescope on Earth had ever achieved. The Great Red Spot was not just a single storm. It was a massive, spinning vortex, rotating counterclockwise, interacting with smaller storms around it, pulling them in and swallowing them whole. The winds at its edges blew at hundreds of miles per hour. It was a hurricane with no land to slow it down and no ocean beneath it. Just an endless sky of hydrogen and helium, deeper than any ocean on Earth. The colors of the Great Red Spot, ranging from deep brick red to pale salmon, were created by the complex chemistry of Jupiter's atmosphere. Sunlight breaks apart simple molecules in the upper atmosphere, and the resulting fragments recombine into more complex compounds, producing the rich palette of colors visible in the Voyager images. The exact identity of the chemicals responsible for the red color is still debated, but they probably include phosphorus compounds and complex organic molecules. Beyond the Great Red Spot, the Voyager cameras revealed a world of incredible atmospheric complexity. White oval storms, some of them as large as Earth, chased each other around the planet in alternating bands of eastward and westward winds. Brown barges, dark elongated features in the atmosphere, drifted along the edges of the cloud bands. Bright plumes of ammonia ice crystals erupted from deep within the atmosphere, rising like thunderheads above the surrounding clouds. Lightning bolts, far more powerful than any on Earth, flickered in the dark night-side atmosphere. Jupiter's atmosphere was a laboratory for studying fluid dynamics on a scale that was impossible to replicate on Earth, and the Voyager data provided meteorologists and atmospheric scientists with material that they are still studying today, nearly half a century later. Voyager 1 made its closest approach to Jupiter on March 5, 1979. It came within about 217,000 miles of the planet's cloud tops. During a period of just 48 hours around that closest approach, the spacecraft gathered more data about Jupiter than all previous missions combined. It returned 19,000 photographs. And the discoveries came fast. Jupiter had a ring. No one had known this before. The ring was faint and thin, nothing like the glorious rings of Saturn, but it was there, made of tiny particles of dust knocked loose from Jupiter's inner moons. It was the first hint that ring systems might be common among the giant planets. But the real surprises came from Jupiter's moons. Jupiter has many moons. At the time of the Voyager encounters, scientists knew of 13. The four largest, Io, Europa, Ganymede, and Callisto, had been discovered by Galileo in 1610. They were called the Galilean moons, and even through telescopes, they were little more than points of light. The Voyagers changed that forever. Io was the closest of the 4 large moons to Jupiter. Scientists expected it to be a dead, cratered world, something like our own moon. But when the images came back, the scientists could not believe what they were seeing. Io was alive. Its surface was covered in volcanic eruptions. Plumes of sulfur and sulfur dioxide were shooting hundreds of miles into space. The surface was painted in vivid yellows, oranges, and reds, like a cosmic pizza, some scientists joked. Voyager 1 discovered 9 active volcanoes on Io. When Voyager 2 arrived 4 months later, 8 of those 9 were still erupting. Io was the most volcanically active body in the entire solar system. The reason for all this activity was Jupiter itself. The giant planet's immense gravity, combined with the gravitational pull of the other large moons, was constantly squeezing and stretching Io, generating enormous amounts of heat inside the little moon. It was like kneading a ball of dough. The friction created by this constant flexing kept Io's interior molten, feeding the volcanoes that covered its surface. No one had predicted this. The discovery of active volcanism on Io was actually made by a Voyager navigation engineer named Linda Morabito. She was examining an image of Io taken a few days after the closest approach, looking for background stars to use for navigation calculations, when she noticed a strange bright crescent on the edge of the moon. It was not a star. It was a volcanic plume, rising 170 miles above the surface and catching the sunlight. It was one of the most dramatic discoveries in the history of space exploration, and it happened almost by accident. The discovery transformed our understanding of how moons and planets generate internal heat, and led to the realization that tidal forces can be just as important as radioactive decay in keeping a world geologically active. It was one of the great surprises of planetary science. Europa was next. Where Io was fire and chaos, Europa was ice and mystery. Its surface was the smoothest in the entire solar system. Almost no craters. Instead, Europa was covered in a shell of water ice, crisscrossed with long, dark lines that stretched for thousands of miles. These lines looked like cracks in the ice, and scientists began to wonder if there might be something beneath that ice. An ocean, a vast, liquid ocean kept warm by the same tidal forces that heated Io. If Europa had an ocean of liquid water beneath its frozen surface, it raised one of the most exciting questions in all of science. Could there be life there? Not on the surface, where radiation from Jupiter would destroy anything living, but deep below, in the dark water, warmed by the heat of the moon's interior. On Earth, life thrives in the most extreme environments, near hydrothermal vents on the ocean floor, where superheated water laden with minerals pours out of cracks in the crust. These environments are completely independent of sunlight. They are powered by the heat of the Earth itself. If similar vents existed on the floor of Europa's ocean, they could provide the energy and the chemicals needed to support life. It was a revolutionary idea. Before the Voyagers, the search for life beyond Earth, had focused almost entirely on Mars, a planet with a thin atmosphere and evidence of ancient water. Europa opened up a completely new possibility, that life might exist not on the surfaces of other worlds, but beneath them, hidden in dark oceans under shells of ice. This idea has since been extended to other moons, including Enceladus at Saturn and possibly Ganymede and Callisto as well. The search for life in the outer solar system is now one of the most active areas of planetary science, and it traces its origins directly to the Voyager flybys. we still do not know the answer. But it was the Voyagers that first gave us the reason to ask the question. Ganymede, the largest moon in the solar system, larger even than the planet Mercury, revealed a surface of two distinct types. There were old, dark, heavily cratered regions, and younger, lighter areas crisscrossed with grooves and ridges. The grooves suggested that Ganymede had experienced periods of tectonic activity, where its icy crust had been pulled apart and reformed. It was a world with a complicated history, written in the scars on its face. Callisto, the outermost of the 4 Galilean moons, was the most heavily cratered object the Voyagers had ever seen. Its surface was ancient, battered by billions of years of impacts. One enormous impact basin, called Valhalla, stretched across much of the moon's face, surrounded by concentric rings of cracks that spread outward like ripples in a pond. Callisto seemed to be a time capsule, its surface preserving a record of bombardment that stretched back to the earliest days of the solar system. There was something else about the Galilean moons that the Voyagers revealed, something that would not be fully appreciated for years. Taken together, Io, Europa, Ganymede, and Callisto formed a kind of laboratory for understanding how worlds evolve. They were all born from the same disk of gas and dust that surrounded Jupiter in the early solar system, and yet each one had taken a completely different path. Io, closest to Jupiter, was a world of fire, constantly resurfaced by its volcanoes, with no ancient craters left to tell the story of its past. Europa, the next one out, had an icy shell that was being cracked and shifted by forces from below, hinting at a warm ocean. Ganymede, farther still, had experienced some tectonic activity in its past, but had also preserved large areas of ancient cratered terrain. And Callisto, the farthest of the 4, was a frozen, cratered relic, seemingly unchanged for billions of years. The pattern was clear. The closer a moon was to Jupiter, the more internal heat it had, the more geologically active it was, and the younger its surface appeared. Distance from Jupiter was the key variable, because it determined how strongly each moon was affected by tidal forces. This insight helped scientists understand not just the Jovian system, but also the moons of other giant planets, and even some aspects of how planets around other stars might behave. The Voyagers also made important discoveries about Jupiter's magnetosphere, the vast region of space controlled by the planet's magnetic field. Jupiter has the strongest magnetic field of any planet in the solar system, about 20,000 times stronger than Earth's. This magnetic field traps charged particles from the solar wind and from Io's volcanoes, creating intense radiation belts that are deadly to unprotected electronics and would be lethal to any human who ventured into them. The Voyager spacecraft had been designed with extra shielding to protect their instruments during the Jupiter encounter, based on data from the earlier Pioneer 10 and Pioneer 11 missions. Even so, some instruments experienced temporary malfunctions as they passed through the most intense regions of radiation. The interaction between Jupiter's magnetic field and Io was particularly dramatic. As Io orbits Jupiter, the volcanic gases it releases are ionized by the intense radiation and swept up by the rotating magnetic field, creating a donut-shaped ring of charged particles around Jupiter called the Io plasma torus. This torus generates powerful electrical currents that flow between Io and Jupiter along the magnetic field lines, creating auroras on Jupiter's poles that are hundreds of times more powerful than any aurora on Earth. The Voyagers were the first to study this remarkable system in detail, and their data laid the foundation for decades of follow-up research. Jupiter had given the Voyagers more than anyone had dared to hope. Active volcanoes on Io, a possible ocean beneath the ice of Europa, the largest moon in the solar system, a faint ring of dust, the great red spot in glorious detail, and 3 previously unknown small moons. But the journey was far from over. The gravity of Jupiter had bent the trajectories of both spacecraft, flinging them outward toward the ringed planet. Saturn was next. The trip from Jupiter to Saturn took about 1.5 years. During this time, the spacecraft coasted through the quiet of interplanetary space, their instruments still measuring the solar wind, the magnetic fields, and the streams of charged particles that fill the space between the planets. The sun was growing fainter behind them. Earth was already so distant that radio signals took more than an hour to make the trip. And ahead, growing slowly brighter in the cameras, was Saturn. Saturn is often called the jewel of the solar system, and with good reason. Even through a small telescope on Earth, its rings are breathtaking, a delicate band of light encircling the planet like a halo. For centuries, astronomers had debated the nature of the rings. Were they solid disks? Were they made of gas? In the 19th century, James Clerk Maxwell proved mathematically that the rings could not be solid, but must instead be made of countless individual particles, each one orbiting Saturn like a tiny moon. But until the Voyagers arrived, no one knew just how intricate those particles could arrange themselves. The Voyager cameras revealed something that no telescope had ever shown. The rings were not simple. They were not just a few broad bands of ice and rock. They were incredibly complex. What had looked like 5 or 6 rings from Earth turned out to be thousands of individual ringlets, nested inside one another like the grooves on a phonograph record. Some were bright and dense. Others were thin and almost transparent. Some had sharp edges. Others faded gradually into the surrounding space. And there were features that no one had predicted. The F-ring, the outermost thin ring discovered just a year earlier by the Pioneer 11 spacecraft, appeared to be braided, its strands twisted around one another in a way that seemed impossible under normal gravitational physics. The explanation the Voyagers found was a pair of small moons, one orbiting just inside the ring and one just outside it. These shepherd moons, as scientists called them, used their gravity to keep the ring particles confined in a narrow band. Their gravitational influence also created the strange braided pattern. The Voyagers discovered 3 new moons at Saturn, Atlas, Prometheus, and Pandora, all of them intimately connected with the ring system. Spokes appeared in Saturn's B ring. These were dark, radial features that seemed to rotate with the planet, rather than orbiting at the speed you would expect based on their distance from Saturn. They looked like the spokes on a bicycle wheel, stretching across the ring surface. Scientists debated their cause for years. The best explanation seemed to involve tiny charged particles lifted above the ring plane by electrical forces, creating a dusty haze that cast shadows on the ring below. Voyager 1 arrived at Saturn on November 12, 1980, passing within 77,000 miles of the planet's cloud tops. Its instruments measured the composition of Saturn's atmosphere and found it to be mostly hydrogen, with about 7% helium and traces of other gases. This helium abundance was lower than expected and lower than what had been measured at Jupiter. Scientists concluded that helium might be raining out of Saturn's atmosphere, sinking toward the planet's core as tiny droplets. This process, called helium rain, would generate heat, helping to explain why Saturn radiates more energy than it receives from the Sun. It was one of those elegant connections between observation and theory that makes planetary science so satisfying. The winds were astonishing. On Jupiter, the fastest winds blew at about 400 miles per hour. On Saturn, they reached 100 miles per hour. Saturn's atmosphere was more dynamic than anyone had expected, with storms, jet streams, and complex cloud patterns stretching across the planet's face. But the most important target of Voyager 1's Saturn encounter was not the planet itself. It was Titan, Saturn's largest moon. Titan was the only moon in the solar system known to have a thick atmosphere. From Earth, Titan appeared as an orange, hazy ball, its surface completely hidden beneath a dense layer of smog. Scientists were desperate to know what lay beneath that smog. Was there a solid surface? Lakes, oceans, mountains? Voyager 1 was targeted to make a close flyby of Titan, passing within about 4,000 miles of its surface. The close approach gave the spacecraft's instruments a detailed look at the moon's atmosphere. They found it to be mostly nitrogen, much like Earth's atmosphere, with about 1.5 times the surface pressure of our own planet. There were also traces of methane and other organic compounds, complex carbon-based molecules that are the building blocks of life. The orange haze that covered Titan was made of these organic molecules, a thick photochemical smog created by sunlight breaking apart methane in the upper atmosphere. But Voyager 1's cameras could not see through the haze. The surface of Titan remained hidden. Scientists speculated that lakes or even oceans of liquid hydrocarbons, methane and ethane, might exist on the surface. Decades later, the Cassini-Huygens mission would confirm this, landing a probe on Titan's surface and discovering vast lakes of liquid methane. But it was the Voyagers that first revealed the tantalizing clues. The decision to fly Voyager 1 close to Titan came at a cost. The trajectory required to make the Titan flyby sent Voyager 1 up and out of the plane of the planets. It could no longer visit Uranus or Neptune. Its planetary mission was over. From now on, Voyager 1 would be heading out of the solar system, climbing away from the Sun at a steep angle. But the mission was not over. Far from it. Voyager 1 had begun the longest leg of its journey, the journey to the stars. Voyager 2, meanwhile, had its own encounter with Saturn in August 1981. It flew about 14,000 miles closer to the planet than Voyager 1 had, returning even more detailed images of the rings in the atmosphere. It found that the F-ring, which had appeared to have 3 strands during the Voyager 1 flyby, now had 5. The rings were changing, evolving, responding to the complex gravitational dance of Saturn's many moons. The time between the 2 Voyager encounters was less than a year, but in that short time, the rings had visibly transformed. This was a revelation. Saturn's rings were not the static, unchanging structures they appeared to be from Earth. They were alive with motion and change, constantly being sculpted by the gravity of dozens of moons, some of which were embedded within the rings themselves. The images of the rings revealed structures at every scale, from the broad divisions visible from Earth to the finest ringlets, only a few miles wide, that appeared in the highest resolution photographs. Some of the ring features seemed to be density waves, ripples in the ring material caused by the gravitational pull of Saturn's moons, spreading outward like the waves created by dropping a stone into a pond. Other features were bending waves, where the ring material was pulled slightly out of the ring plane by the gravity of moons orbiting at an angle. These wave patterns allowed scientists to measure the mass and thickness of the rings with remarkable precision. Saturn's main rings, despite their enormous breadth, turned out to be astonishingly thin, in some places only about 30 feet thick, no thicker than a 2-story building. Voyager 2 also studied several of Saturn's other moons. Mimas, a small moon only about 250 miles across, had an enormous impact crater named Herschel that was nearly a third the diameter of the moon itself. The crater was so large, relative to the size of the moon, that it made Mimas look like the Death Star from Star Wars, a resemblance that delighted scientists and the public alike. Enceladus, another small moon, showed a surface that was remarkably smooth in places, with very few craters. This suggested that the surface had been renewed relatively recently by some internal process, perhaps cryovolcanism, the eruption of water or other ices from below the surface. Later missions would confirm that Enceladus has geysers of water ice shooting into space from cracks near its south pole, fed by a subsurface ocean. Iapetus had one hemisphere that was bright white and another that was coal black, a mystery that took decades to explain. Hyperion was an oddly shaped sponge-like moon that tumbled chaotically as it orbited Saturn, its rotation never settling into a predictable pattern. Saturn had been generous with its secrets, the complexity of its rings, the thickness of Titan's atmosphere, the volcanic activity hinted at on Enceladus, the strange moons with their strange surfaces. And now it was time for Voyager 2 to do something that no spacecraft had ever done. It was time to visit Uranus. The journey from Saturn to Uranus took 5.5 years. 5.5 years of coasting through the darkness, the sun growing smaller and dimmer behind it. By the time Voyager 2 reached Uranus in January 1986, the spacecraft was so far from the sun that the light levels were only about a quarter of what they had been at Saturn. Engineers on Earth had to reprogram the spacecraft's computers to compensate, developing new techniques to take clear photographs in the dim light. Exposure times were increased to 15 seconds, and a special image motion compensation technique was programmed into the spacecraft to prevent the pictures from blurring as the probe sped past. Uranus was a world lying on its side. Its axis of rotation is tilted nearly 98 degrees, so that it essentially rolls around the sun like a ball. No one knows exactly why Uranus is tilted so far. The most popular theory is that a massive collision with an Earth-sized object early in the planet's history knocked it over. This collision would have been tremendously violent, releasing enough energy to melt much of the planet's interior. Some scientists have suggested that the tilting impact may have also affected the planet's internal heat, explaining why Uranus radiates very little energy compared to the other giant planets. Because of this extreme tilt, the Voyager 2 encounter was like nothing the mission had experienced before. The planet's moons and rings formed a giant target, like a bullseye, and the spacecraft had to fly straight through it. There was no time for the leisurely multi-day observations that had been possible at Jupiter and Saturn. Voyager 2 had only about 5.5 hours of close study as it raced through the Uranian system. But those few hours were enough to transform our understanding of Uranus. The planet's atmosphere, viewed in natural light, appeared as a bland, featureless blue-green ball. There were no dramatic storms, no colourful bands, nothing like the swirling chaos of Jupiter or Saturn. But when the images were processed with false colour to enhance subtle differences, faint bands of clouds became visible, circling the planet in concentric rings around its south pole, which at that time was pointed directly at the sun. The temperature of the atmosphere was measured at about -357 degrees Fahrenheit, making Uranus the coldest planet in the solar system, even colder than Neptune, which is farther from the sun. Scientists found this puzzling and suggested that Uranus might have less internal heat than the other giant planets, possibly because of the same cataclysmic impact that tilted it on its side billions of years ago. Voyager 2 found 10 previously unknown moons at Uranus, bringing the total from 5 to 15. Several of these new moons were intimately connected with the ring system. Cordelia and Ophelia, two tiny moons orbiting on either side of the outermost ring, called the Epsilon ring, acted as shepherd moons, their gravity keeping the ring particles confined in a narrow band. The moons were named after characters from Shakespeare, continuing a tradition that had been established when Uranus's first moons were discovered in the 18th century. The Voyager spacecraft also discovered 2 new rings, in addition to the 9 that had been found from Earth in 1977. The ring system was distinctly different from those of Jupiter and Saturn. The Uranian rings were narrow, dark, and widely spaced, made of large, dark particles, rather than the bright, icy particles that make up Saturn's rings. Scientists speculated that the rings might be relatively young, perhaps the remnants of a moon that was shattered by an impact or torn apart by tidal forces. But the biggest surprise at Uranus came from its magnetic field. Every planet with a magnetic field that had been studied before Uranus had its magnetic poles roughly aligned with its geographic poles. Earth's magnetic field, for example, is tilted about 11 degrees from its rotation axis. At Uranus, the magnetic field was tilted a stunning 55 to 60 degrees from the rotation axis, and it was not even centered on the planet. The center of the magnetic field was offset from the center of Uranus by about 1/3 of the planet's radius. This was completely unexpected. It meant that the magnetic field of Uranus was not generated in the planet's core, as it is on Earth. Instead, it seemed to be produced at an intermediate depth, in a layer where water becomes electrically conductive under extreme pressure. The misalignment between the magnetic field and the rotation axis also created a bizarre corkscrew-shaped magnetotail that trailed behind the planet as it moved through space, twisting and spiraling as Uranus rotated. The 5 large moons of Uranus, Miranda, Ariel, Umbriel, Titania, and Oberon were each unique. Miranda, the smallest and closest to the planet, was the biggest surprise. Its surface was a patchwork of different types of terrain, jumbled together as if the moon had been assembled from spare parts. There were enormous cliffs, some of them 12 miles deep, the deepest known in the solar system. There were large oval features called coronae, surrounded by ridges and grooves. Some areas of the surface were old and heavily cratered. Others were young and smooth. One theory suggested that Miranda might have been shattered by a catastrophic impact and then reassembled from the pieces, with different types of material ending up mixed together on the surface. Another theory proposed that Miranda's interior had experienced unusual convection patterns, with warm material rising and cold material sinking in a way that created the strange surface features. Either way, Miranda was a world that defied easy explanation. Ariel showed the most evidence of geological activity among the larger moons. Its surface had long, deep valleys that appeared to be grabens, features created when the crust is pulled apart by tectonic forces. Some of these valleys were partially filled with smooth material, perhaps ice that had flowed in from below. Umbriel was the darkest of the 5, with a uniformly grey surface and few bright features. Titania, the largest of the Uranian moons, had long fault valleys and modest surface features. Oberon, the outermost, showed a surface dominated by impact craters, some with dark material on their floors that might have been icy slush pushed up from the interior during the impacts. Voyager 2 left, Uranus behind, and headed for its final planetary encounter, Neptune, the last stop on the Grand Tour. The journey from Uranus to Neptune took 3.5 years. By the time Voyager 2 arrived in August 1989, the spacecraft was 12 years old and more than 2.7 billion miles from the Sun. Light levels were only about 1% of what they are on Earth. Engineers had once again reprogrammed the spacecraft's computers and cameras, squeezing every bit of performance from the aging hardware. The round-trip communication time was more than 8 hours. If something went wrong, there would be no way to fix it quickly. Neptune had been a mystery. Being so far from the Sun, many scientists expected it to be a cold, featureless world, shrouded in a bland, unchanging atmosphere. They could not have been more wrong. When the images came back from Voyager 2, Neptune was spectacular. Its atmosphere was a deep, vivid blue, colored by methane in the upper layers that absorbed red light and reflected blue. And there were storms, big ones. The most dramatic was the Great Dark Spot, an enormous storm system in the southern hemisphere that was about the size of Earth. It looked similar to Jupiter's Great Red Spot, a vast, swirling anticyclone, dark against the blue background. Nearby, bright white clouds of methane ice crystals raced around the planet at tremendous speeds, and the winds. Neptune had the fastest winds in the solar system. They blew at speeds of up to 100 miles per hour, far faster than any winds on Jupiter, Saturn, or Uranus. This was deeply puzzling. Neptune receives very little energy from the Sun. So, where was the energy coming from to drive such powerful winds? The answer seemed to lie in the planet's interior. Neptune radiates more than twice as much energy as it receives from the Sun, suggesting that it has a significant source of internal heat. This internal heat drives the atmospheric circulation, creating the violent winds and storms that Voyager 2 observed. The Great Dark Spot, despite its resemblance to Jupiter's Great Red Spot, turned out to be a very different kind of storm. When the Hubble Space Telescope observed Neptune a few years after the Voyager flyby, the Great Dark Spot had vanished. Unlike Jupiter's Great Red Spot, which has persisted for centuries, Neptune's storms appear to come and go, forming and dissolving on timescales of years. New dark spots have appeared and disappeared since then, suggesting that Neptune's atmosphere is even more dynamic than Voyager's brief flyby could reveal. The bright white clouds near the Great Dark Spot were made of methane ice crystals, condensing in the colder air at the tops of the storm system, like cirrus clouds forming above a thunderstorm on Earth. These companion clouds cast shadows on the blue atmosphere below, and the shadows helped scientists estimate the altitude of the clouds above the main cloud deck. Voyager 2 also precisely measured Neptune's rotation period, using radio emissions generated by the planet's magnetic field. Neptune rotates once every 16 hours and 7 minutes. This was important because it settled a question that had been debated for years, since ground-based observations of Neptune's atmosphere had given inconsistent rotation periods, confused by the different speeds of the atmospheric winds at different latitudes. Neptune's magnetic field turned out to be just as strange as the one at Uranus. It was tilted 47 degrees from the rotation axis and offset from the planet's center by about half a planetary radius. This similarity to Uranus suggested that the unusual magnetic field geometry might be a common feature of ice giant planets, related to the internal structure of these worlds, rather than any peculiarity of Uranus's extreme axial tilt. Voyager 2 discovered 6 new moons at Neptune and found 4 rings, some of which appeared clumpy and incomplete, with bright arcs where the ring material was concentrated. These arcs had been detected from Earth and some astronomers had thought they might be incomplete ring arcs rather than full rings. Voyager 2 showed that the rings were complete, but that the material in them was not evenly distributed. The clumpy distribution was likely maintained by the gravitational influence of nearby moons. But the most stunning discovery at Neptune was not the planet itself. It was Triton, Neptune's largest moon. Triton is a world unlike any other in the solar system. For one thing, it orbits Neptune backwards. Its retrograde orbit, moving in the opposite direction to Neptune's rotation, strongly suggested that Triton had not formed alongside Neptune, but had been captured from the outer solar system. Triton may have once been an independent world, similar to Pluto, wandering through the cold reaches beyond Neptune until Neptune's gravity captured it. The capture process would have been violent, involving enormous tidal forces that heated Triton's interior and may have melted much of its ice. Over millions of years, tidal friction would have circularized Triton's originally elliptical orbit, and the moon would have gradually cooled, refreezing from the outside in. Triton is one of the coldest objects in the solar system, with a surface temperature of about -391 degrees Fahrenheit. Its surface is made mostly of frozen nitrogen, with traces of methane, carbon monoxide, and water ice. Despite these frigid conditions, Triton showed clear evidence of geological activity. The lack of impact craters on much of its surface meant that the surface had been renewed relatively recently in geological terms, within the last few 100 million years. Voyager 2 passed within about 25,000 miles of Triton, close enough to see remarkable details on its frozen surface. The southern hemisphere was covered in a terrain unlike anything seen before. Scientists described it as cantaloupe terrain because it looked like the skin of a cantaloupe melon, covered in a network of rounded depressions and ridges. Very few impact craters were visible in this region, suggesting that the surface was relatively young and had been reshaped by some geological process. And then there were the geysers. Voyager 2 discovered dark plumes rising from Triton's surface, shooting material 5 miles into the thin nitrogen atmosphere and leaving long, dark streaks on the surface as the particles were carried downwind. These were not volcanic eruptions in the traditional sense. They were powered by sunlight. The sun, even at Neptune's enormous distance, was warming patches of frozen nitrogen beneath a thin, transparent layer of nitrogen ice. As the nitrogen warmed and turned to gas, the pressure built up until it exploded through the surface in a geyser of gas and dark particles. It was an entirely new type of geological activity, one that no one had predicted. The dark streaks left by the geysers extended for miles across the pinkish-white surface of Triton's south polar region, all pointing in the same direction, carried by the faint winds of the moon's thin atmosphere. At least 4 active geysers were identified, though there may have been more that were not visible during the brief flyby. Triton was not dead. It was alive with processes that we had never imagined. With the Neptune encounter, Voyager 2's planetary mission was complete. The Grand Tour, the dream that had been born in the 1960s, the plan that had been scaled back and almost cancelled, was finally finished. 2 spacecraft had visited 4 planets. They had discovered dozens of new moons. They had revealed the complexity of ring systems, the violence of volcanic moons, the possibility of oceans beneath icy shells, and the fierce beauty of worlds that had never been seen up close. They had changed everything we thought we knew about the outer solar system. In 12 years, the Voyagers had returned more than 100,000 photographs and an ocean of scientific data. They had discovered 22 new moons between the two missions. They had found rings around Jupiter and studied the rings of Saturn, Uranus, and Neptune in detail that transformed our understanding of these delicate structures. They had revealed that every planet and every moon in the outer solar system was unique, with its own personality, its own history, its own mysteries. Before the Voyagers, the outer planets were little more than blurry dots in our telescopes. After the Voyagers, they were worlds, as real and as varied as the Earth and Moon. The cost of the Voyager program, from design through the Neptune encounter, was about $865 million. That sounds like a lot of money, but it works out to less than $5 per person in the United States, spread over more than a decade. For the price of a fast food meal, every American got the exploration of 4 planets, dozens of moons, and the first look at the space between the stars. It is difficult to think of a better bargain in the history of human endeavor. But the Voyagers were not done. Their planetary work was finished, but a new mission was about to begin, the Voyager Interstellar mission, and it would take them to places even more strange and surprising than the planets they had left behind. Before we follow the Voyagers into the space between the stars, there is one more moment from the planetary mission that deserves our attention. It happened on February 14, 1990, Valentine's Day. Voyager 1 was by now more than 3.7 billion miles from Earth, already well past the orbit of Pluto. Its cameras had been turned off after the Saturn encounter in 1980 to save power. But the astronomer Carl Sagan, who had been a member of the Voyager imaging team from the beginning, had an idea. He wanted Voyager 1 to turn its camera around, point it back toward the inner solar system, and take one last picture, a family portrait, a farewell snapshot of the worlds it had left behind. NASA agreed. On February 13, 1990, commands were sent to Voyager 1, traveling for more than 5 hours at the speed of light to reach the distant spacecraft. The cameras were warmed up for 3 hours, and then, over the course of the next few hours, Voyager 1 took 60 photographs, pointing its camera at Neptune, Uranus, Saturn, the Sun, Jupiter, Earth, and Venus. Mercury and Mars were too close to the Sun's glare to be seen. The images took weeks to transmit back to Earth. The data was stored on Voyager 1's onboard tape recorder and then sent home in multiple communication passes with the Deep Space Network. The transmission was delayed because the Magellan mission to Venus and the Galileo mission to Jupiter were given priority use of the tracking antennas. It was not until May 1st, 1990, that all the image data had arrived on Earth. When they arrived, most of them showed only the faint dots of distant planets against the blackness of space. But one of them became one of the most famous photographs in human history. In one frame, Earth appeared as a tiny point of light, less than a single pixel across, suspended in a beam of scattered sunlight. A pale blue dot. Carl Sagan wrote about that image. He said that everyone you have ever loved, everyone you have ever known, everyone who ever lived out their lives on that tiny dot. Every king and peasant, every saint and sinner, every young couple in love, every mother and father, every inventor and explorer, every teacher of morals, every corrupt politician, every hero and coward, all of it on a mote of dust suspended in a sunbeam. The photograph changed the way many people thought about Earth and about themselves. It was not the first photograph of Earth from space. The Apollo astronauts had taken the famous Earthrise photograph in 1968, showing our planet rising above the lunar horizon, and the blue marble photograph in 1972, showing the full disk of Earth from about 18,000 miles away. But those images showed Earth as a recognizable world with continents and oceans and clouds. The pale blue dot showed Earth as it truly is in the context of the cosmos, a tiny, insignificant speck, barely visible against the vastness of space. It was not a photograph that made you feel proud or powerful. It was a photograph that made you feel small. And in that smallness, there was a kind of liberation. If we are that small, then our differences are even smaller. Our borders, our conflicts, our hatreds, our divisions, all of them are invisible from the distance of a few billion miles. All that is visible is a pale blue dot, a small blue world, the only home we have ever known. The photograph was a reminder of how small we are, and how precious our world is, and how foolish our divisions seem when viewed from such a distance. 34 minutes after taking that photograph, Voyager 1 turned off its cameras forever. It would not need them anymore. There was nothing ahead to photograph, only the vast, empty darkness between the stars, and a journey that would last longer than human civilization. After the cameras were powered down, the Voyagers entered what NASA called the Voyager Interstellar mission. The goal was simple in concept and staggering in scope. The spacecraft would continue outward, away from the Sun, measuring the environment around them until they crossed the boundary between the solar system and interstellar space. And then they would keep going, exploring a region that no human-made object had ever reached. To understand what the Voyagers found, we need to understand the structure of the heliosphere. The Sun is not just a ball of light in the sky. It is a nuclear furnace that is constantly pouring energy and matter into space. The solar wind, a stream of charged particles, mostly protons and electrons, flows outward from the Sun in all directions at speeds of up to 1 million miles per hour. This wind creates a vast bubble around the Sun, inflating it like a balloon against the pressure of the interstellar medium, the thin gas and dust that fills the space between the stars. This bubble is the heliosphere. It extends far beyond the orbit of Pluto, enclosing the entire solar system in a cocoon of solar particles and magnetic fields. The heliosphere has a structure like an onion with layers. Close to the Sun, the solar wind is strong and fast. As it moves outward, it gradually loses speed and density. Eventually, at a boundary called the termination shock, the solar wind slows down abruptly, like a river hitting a dam. Beyond the termination shock is a region called the heliosheath, where the slowed solar wind is compressed and turbulent, jostled by the pressure of the interstellar medium pressing in from outside. And beyond the heliosheath is the heliopause, the outermost boundary of the heliosphere, where the solar wind finally stops and the interstellar medium begins. For decades, scientists had theorized about these boundaries, but no one knew exactly where they were or what they looked like. The Voyagers were about to find out. The journey from Neptune's orbit to the termination shock was immensely long. For 15 years after its last planetary encounter, Voyager 1 coasted outward through the solar wind, measuring the gradual changes in the flow of charged particles and the slowly weakening magnetic field. The Sun's influence was fading, but it was fading slowly. Space is vast, and the termination shock was far away. During these quiet years, the Voyager science teams continued to monitor the data, watching for any sign that the spacecraft was approaching the boundary. They looked for changes in the intensity of cosmic rays, which should increase as the protective bubble of the heliosphere thinned out. They measured the speed and temperature of the solar wind, which should change as the wind approached the termination shock, and they waited. In the early 2000s, signs began to appear. The solar wind was slowing down. Cosmic ray intensities were rising. The magnetic field was becoming more compressed. Something was happening ahead. Voyager 1 reached the termination shock in December 2004, at a distance of about 8.7 billion miles from the Sun. The crossing was not a clean, sudden event. The boundaries seemed to fluctuate, moving inward and outward as the Sun's activity changed. The spacecraft passed through a region where the solar wind particles suddenly slowed from supersonic to subsonic speeds, and the temperature of the particles jumped dramatically. It was like hitting a wall of heat. The solar wind had been cooled by its long journey outward, but at the termination shock, it was suddenly compressed and heated. Voyager 2 reached the termination shock in August 2007, at a slightly different distance from the Sun, about 8.3 billion miles. The fact that the two spacecraft hit the termination shock at different distances confirmed that the heliosphere is not a perfect sphere. It is asymmetric, pushed and pulled by the pressure of the interstellar medium, which itself is not uniform. The heliosphere breathes, expanding and contracting as the Sun goes through its 11-year cycle of activity. Beyond the termination shock, the Voyagers entered the heliosheath. This region was turbulent and chaotic. The solar wind, now moving slowly, was being pushed and squeezed by the interstellar medium. The magnetic field was compressed and distorted. The temperature of the plasma was much higher here than in the freely flowing solar wind inside the termination shock, heated by the compression. It was like a traffic jam. The solar wind particles, moving outward at high speed, suddenly hit the termination shock and slowed down, piling up and heating up as they crowded together. Voyager 1 spent 8 years crossing the heliosheath, from 2004 to 2012. During that time, it measured a gradually changing environment. The intensity of cosmic rays from outside the solar system slowly increased, as the shielding effect of the heliosphere grew weaker. The direction of the magnetic field shifted and fluctuated, sometimes suddenly. And then, in 2010, Voyager 1 detected something unexpected here. A region where the magnetic field lines seemed to form bubbles, like the froth on top of a wave. Scientists called this region the magnetic highway, a zone where particles from inside and outside the heliosphere were mixing, trading places, seeping through the boundary in both directions. The heliosphere, it seemed, was not a sealed bubble. It was permeable, leaking particles outward and allowing cosmic rays to seep inward. Then, on August 25, 2012, Voyager 1 crossed the heliopause. The crossing was dramatic. The spacecraft's instruments detected a sudden drop in the number of solar wind particles and a sharp increase in the number of galactic cosmic rays, high-energy particles that originate outside the solar system, from exploding stars and other violent events elsewhere in the galaxy. These two measurements together told scientists that Voyager 1 had left the heliosphere and entered interstellar space. It was the first human-made object to do so. The announcement did not come immediately. It took over a year for scientists to be fully confident that Voyager 1 had actually crossed the boundary. The difficulty was that the spacecraft's plasma science instrument, which could have provided a definitive measurement, had stopped working decades earlier. Without it, scientists had to rely on indirect evidence, particularly the plasma wave instrument, which could infer the density of the surrounding plasma from the oscillations it detected. In April 2013, about 8 months after the crossing, a powerful burst of solar energy reached Voyager 1's location and excited the interstellar plasma, causing it to vibrate. The frequency of that vibration told scientists that the plasma density around Voyager 1 was about 40 times higher than it had been inside the heliosphere. That was the smoking gun. Voyager 1 was swimming in interstellar plasma, not solar plasma. It had crossed the threshold. But the crossing also brought a surprise. The plasma, the thin electrically charged gas that fills both the heliosphere and interstellar space, was far hotter than expected. The temperatures at the heliopause were measured at between 30,000 and 50,000 Kelvin. That is roughly 54,000 to 90,000 degrees Fahrenheit, hotter than the surface of most stars. Scientists called it a wall of fire, though it was a fire you could walk through without feeling a thing. The reason is density. The plasma at the heliopause is incredibly thin. There are so few particles per cubic meter that even though each individual particle is moving at tremendous speed, carrying enormous energy, the total amount of heat they can transfer to a physical object is negligible. The Voyager spacecraft sailed through this wall of fire completely unharmed. Why is the boundary so hot? The answer lies in the collision between the solar wind and the interstellar medium. As the solar wind slows down and piles up at the edge of the heliosphere, it compresses and heats the plasma. Magnetic field lines from both the Sun and the interstellar medium get tangled together, and magnetic reconnection events, where field lines snap and reform, convert enormous amounts of magnetic energy into heat. Imagine two rubber bands stretched tight and then released, so they snap against each other. The energy stored in the tension of the rubber bands is converted into motion and heat. Magnetic reconnection works on a similar principle, but on a scale that spans millions of miles. The field lines from the Sun and from the galaxy meet at the heliopause, and when they reconnect, the energy released heats the surrounding plasma to those astonishing temperatures. This process is not unique to our solar system. Magnetic reconnection happens all over the universe, in the coronae of stars, in the accretion disks around black holes, in the tails of planetary magnetospheres. But the heliopause gave us the first chance to study it, in a natural boundary between two different magnetic environments, and the Voyagers were the instruments that made it possible. The data they collected has helped refine computer models of magnetic reconnection that are used in many different areas of astrophysics, from understanding solar flares to predicting space weather near Earth. The result is a seething invisible barrier of superheated plasma at the edge of our solar system, a boundary that has been there for as long as the Sun has existed, and that we only discovered because two small spacecraft, built in the 1970s, were brave enough to go and look. Voyager 2 crossed the heliopause on November 5, 2018, 6 years after its twin. It crossed at a different point, in a different direction, at a different distance from the Sun. And its measurements confirmed what Voyager 1 had found. The temperatures were in the same range. The magnetic field direction outside the heliosphere was the same, parallel to the field inside, a finding that surprised scientists because they had expected the interstellar magnetic field to point in a different direction. But with data from two spacecraft at two different locations, they could now confirm that this alignment was not a coincidence. It was a real feature of the boundary between our solar system and the galaxy beyond. Voyager 2 also found something that Voyager 1 had not been able to measure. Because Voyager 2 still had a working plasma science instrument, it could directly measure the properties of the plasma on both sides of the heliopause. It found that the heliopause was not a sharp, clean boundary. It was a transition zone, a region where particles from inside and outside the heliosphere mixed together. On the interstellar side, the spacecraft detected a leakage of solar particles that had somehow made it through the boundary. The heliosphere was not a sealed wall. It was more like a membrane, letting some things through while blocking others. At the point where Voyager 2 crossed, this leakage was more pronounced than at the point where Voyager 1 had crossed, suggesting that some parts of the heliosphere are more permeable than others. Now, both Voyagers were in interstellar space, the space between the stars, a region that no human eye has ever seen, no human instrument has ever measured, until these two small machines arrived, and they began to hear something. A sound that no one had expected, a hum. In 2021, scientists studying data from Voyager 1's plasma wave instrument made a discovery. The instrument, which detects vibrations in the plasma surrounding the spacecraft, had been picking up a faint, persistent signal since about 2017. It was a low-frequency hum, steady and monotone, at a frequency of about 3 kHz. It was nothing like the louder, more dramatic bursts of plasma oscillation that the instrument had detected earlier, which had been caused by shock waves from solar eruptions traveling all the way out to interstellar space. This new signal was different. It was constant. It was always there. It was the background noise of the interstellar medium itself. Stella Koch-Ocker, a doctoral student at Cornell University, was the one who found it. She was staring at a plot of the data when she noticed something very faint. A thin, persistent line. At first she was not sure if it was real, but it was. It was the sound of the space between the stars, a gentle, unceasing vibration of the sparse plasma that fills the galaxy. Ocker described it as very faint and monotone, like a single steady note playing constantly but changing very slightly over time. This hum turned out to be incredibly useful. The frequency of the plasma oscillations is directly related to the density of the plasma. By measuring the hum, scientists could track the density of the interstellar medium along Voyager 1's path, creating the most complete map of interstellar plasma density ever made. They found that the density had been gradually increasing since 2013, rising about 40-fold by 2015, and then remaining relatively stable with some fluctuations. This was unexpected. If the interstellar medium were uniform, the density should stay roughly constant. The changing density suggested that Voyager 1 was moving through regions of space with different properties, perhaps influenced by the Sun's heliosphere, pushing against the interstellar medium, creating ripples and waves that the spacecraft was now swimming through. The plasma wave instrument works by detecting the vibrations of electrons in the ionized gas that surrounds the spacecraft. The instrument has two long antennas, each extending about 30 feet behind the spacecraft, shaped like rabbit ears. These antennas pick up the electrical oscillations of the plasma and convert them into signals that can be transmitted back to Earth. When those signals are converted into audio, they produce an eerie, otherworldly sound, a rising and falling tone that changes pitch as the density of the plasma changes. The denser the plasma, the higher the pitch. When Voyager 1 was inside the heliosphere, the tones were low, around 300 Hz. When it crossed into interstellar space, the frequency jumped to between 2 and 3 kHz, corresponding to the much denser plasma of the interstellar medium. Scientists have released recordings of these sounds, and they are haunting. They sound like nothing you have ever heard, a voice from the edge of nowhere, singing the density of the void. The hum also told scientists that the interstellar medium is not as quiet as they had thought. Even without the dramatic shock waves from the Sun, there is a constant, low-level activity in the gas between the stars. One scientist described it by comparing it to rain. The occasional bursts of plasma oscillation caused by solar eruptions are like lightning strikes in a thunderstorm. The persistent hum is like a gentle rain, always falling, always present. The discovery of the hum means that Voyager 1 can continue to measure the density of the interstellar medium continuously, rather than waiting for the occasional solar shockwave to provide a data point. As the spacecraft moves ever deeper into interstellar space, it will provide an ongoing record of the properties of the medium it passes through, a long, unbroken measurement of the galaxy's local weather. As one scientist put it, the craft is saying, "Here is the density I am swimming through right now, and here it is now, and here it is now." While Voyager 1 was making its way through the heliosheath and eventually crossing into interstellar space, the engineering teams on Earth were fighting a constant battle to keep the aging spacecraft alive. And this battle is the heart of our story tonight, because the signal that Voyager 1 sends us, that thin thread of radio connecting us to the edge of the solar system, depends on power. And the power is running out. The Voyagers are powered by radioisotope thermoelectric generators, devices that convert the heat from decaying plutonium-238 into electricity. When the spacecraft launched in 1977, each generator produced about 470 watts of power. But plutonium-238 decays over time, and the generators lose about 4 watts of power every year. By 2025, each spacecraft had only enough power to run a handful of instruments. The mission team has had to make painful choices, shutting down instruments one by one to keep the most important ones running. In February 2025, NASA shut down the cosmic ray subsystem on Voyager 1. This instrument had been measuring high-energy particles from outside the solar system for nearly 5 decades, and its data had been crucial in confirming that Voyager 1 had entered interstellar space, but there was not enough power to keep it running. It was like losing one of your senses. Voyager 1 could no longer taste the cosmic rays streaming in from distant supernovae. The low-energy charged particle instrument was scheduled to be shut off in 2026. Each shutdown brings Voyager 1 one step closer to silence. The goal was to keep at least the magnetometer and the plasma wave subsystem running for as long as possible, perhaps into the 2030s. These are the instruments that listen to interstellar space, that feel the magnetic fields and hear the hum of the plasma. They are Voyager 1's last remaining sensors. When they go dark, the spacecraft will still be there, still moving, still carrying its golden record, but it will no longer be able to tell us what it is experiencing. The last signal will have been sent. The thruster systems that keep the spacecraft pointed toward Earth have also degraded over the decades. The hydrazine fuel lines have been slowly clogging, making some thrusters unusable. In May 2025, engineers performed a remarkable feat. They revived a set of backup roll thrusters on Voyager 1 that had been out of service since 2004. The thrusters had not been used for over 20 years, and there was no guarantee they would work. The process required heating the frozen fuel lines and carefully testing each thruster, all from a distance of more than 15 billion miles, with commands taking nearly a full day to reach the spacecraft. The fix was completed just in time. The giant antenna in Canberra, Australia, the only antenna on Earth powerful enough to send commands to the Voyager probes, was about to go offline for major upgrades that would last until early 2026. The fact that these spacecraft, built with technology from the mid-1970s, are still operating in 2025 is nothing short of extraordinary. Their computers have about 70 kilobytes of memory. That is less than a single small image on a modern smartphone. They send data back to Earth at a rate of 160 bits per second, roughly the speed of a dial-up internet connection from the 1990s. Their signals, traveling at the speed of light, take more than 22 hours to reach Earth from Voyager 1. And yet, every day, the Deep Space Network listens, and every day, the Voyagers answer. The resilience of this machine has been tested many times over the decades. In late 2023, Voyager 1 nearly died. It began sending back garbled data. The telemetry was gibberish, unreadable, and the team feared the worst. For weeks, the engineers did not know if they would ever hear from Voyager 1 again. Was this the last signal? Had the journey finally ended? The problem turned out to be a corrupted memory chip in the flight data subsystem, one of the spacecraft's 3 computers. Normally, this would be a mission-ending failure, but the Voyager engineers, some of whom have been working on the mission for decades, refused to give up. They found a way to redistribute the corrupted code to other areas of memory, essentially teaching the spacecraft's ancient computer to work around the damaged chip. It took months of careful work, with each command taking nearly a full day to reach the spacecraft, and another day for the response to return. But by April 2024, Voyager 1 was sending back clear data again. The signal had been saved, not the last signal. Not yet. Then, in October 2024, another scare. During a routine command, Voyager 1 unexpectedly switched off one of its 2 radio transmitters, leading to a temporary loss of contact. For several tense days, the spacecraft did not respond to signals from Earth. The control room waited. Was this it? Had the transmitter failed permanently? But by late October, the team managed to restore communications and confirm that the spacecraft was healthy. Once again, the last signal had been postponed. These close calls have become more frequent as Voyager 1 ages, each one a reminder that the end could come at any time, without warning, from any of the thousands of components that have been exposed to the radiation and cold of deep space for nearly 5 decades. Each time the signal returns, there is relief, and each time, the team knows that one day the signal will not return. In November 2026, Voyager 1 is expected to reach a distance of 1 light day from Earth. That means a signal traveling at the speed of light will take a full 24 hours to make the trip from our planet to the spacecraft. 1 light day is about 16 billion miles. It is a number that is almost impossible to comprehend. And yet the spacecraft will still be well within the gravitational influence of the Sun. It will not reach the inner edge of the Oort cloud, the vast shell of icy objects that marks the true outer limit of the Sun's gravitational kingdom, for another 300 years, and it will take about 30,000 years to pass all the way through it. The distances involved in interstellar travel are humbling, even for a spacecraft traveling at 38,000 miles per hour. The Oort cloud is a theoretical sphere of trillions of icy objects that surrounds the solar system at distances ranging from about 2,000 to 100,000 astronomical units from the Sun. 1 astronomical unit is the distance from the Earth to the Sun, about 93 million miles. So the outer edge of the Oort cloud may extend almost halfway to the nearest star. No spacecraft has ever visited the Oort cloud, and no telescope has ever directly observed it. Its existence is inferred from the orbits of long-period comets, which seem to originate from this distant reservoir. The objects in the Oort cloud are thought to be remnants from the formation of the solar system, icy bodies that were flung to the outer reaches by the gravitational interactions of the giant planets billions of years ago. When the Voyagers finally reach the Oort cloud, They will be the first human-made objects to enter this vast, cold shell of primordial ice. But by then, they will have been silent for centuries, their power long exhausted, their instruments dark. But the Voyagers are patient travelers. They do not need to hurry. They will drift through the galaxy for millions, perhaps billions of years, long after their power has failed, long after their instruments have gone silent, long after the last signal has been sent and the last command has been received. They will become silent, frozen artifacts, tumbling slowly through the dark, carrying their golden records and their memories of a small blue world that once reached out to touch the stars. Let us talk about those golden records. They deserve a story of their own. In the spring of 1977, with the Voyager launches only months away, NASA gave astronomer Carl Sagan an unusual assignment: design a message for extraterrestrial civilizations. Sagan had some experience with this. He and his colleagues had designed the Pioneer plaques, small metal engravings placed on the Pioneer 10 and Pioneer 11 spacecraft that carried simple drawings of a man and a woman, a diagram of the solar system, and a map showing Earth's position relative to nearby pulsars. The plaques had been controversial. Some people objected to the nudity of the figures. Others questioned whether any alien could ever decode the message. For the Voyager mission, Sagan wanted to do something more ambitious, much more ambitious. He assembled a small team, including the astrophysicist Frank Drake, the journalist and science writer Timothy Ferris, the artist John Lomberg, the greetings organizer Linda Salzman, and a young creative director named Anne Druyan, who would later become Sagan's wife. They had 6 weeks and a budget of about $1,500 to create a message for the cosmos. The team decided on a phonograph record, a 12-inch disc made of gold-plated copper that could hold both audio and visual information. The choice of a record might seem quaint today, but it was practical. A phonograph record was durable, lightweight, and could survive the harsh conditions of space for millions of years. The gold plating was chosen not for its beauty, but for its resistance to corrosion. Gold does not tarnish, does not oxidize, does not react with the thin gases of interstellar space. A gold-plated record could survive for 1 billion years or more without significant degradation. The records were manufactured by a company in Boulder, Colorado. The master lacquers were cut at the JVC Cutting Center, and the final gold-plated pressings were made by the James G. Lee Record Processing Center in California. 8 records were produced in total, 2 for the spacecraft and 6 for archives. Each record was placed in a protective aluminum jacket that also served as a mounting bracket. The record was enclosed in a protective aluminum jacket, and attached to the jacket was a cartridge and a stylus. Instructions, written in a symbolic language based on the physics of hydrogen atoms, explained how to play the record and how to decode the images encoded in its grooves. The visual information came first. 115 images encoded in analog form, made up of 512 vertical lines each. The images were chosen not for their beauty, but for the amount of information they conveyed. The selection process was intense. The team had to decide which aspects of life on Earth were most important to communicate to a civilization that might know nothing about us. They debated for weeks over which photographs to include and which to leave out. Some choices were straightforward, others were agonizing. Should they include images of war, of poverty, of disease? In the end, they decided against images of conflict, reasoning that the record was meant as a friendly greeting, not a confession of our failings. but they did include images that showed the full range of human experience, from the simple to the complex, from the natural to the technological. They began with mathematical definitions, circles, and simple diagrams, establishing a common language. Then they moved to images of our solar system, of the sun, of the Earth from space. There were photographs of the structure of DNA, of human cells, of a fertilized egg and a developing fetus. There were pictures of people, men and women and children from different parts of the world, of different ages and different skin colors. There were images of people eating, drinking, and nursing babies. There were photographs of buildings, houses, huts, and the Taj Mahal, chosen in part because it was built as a monument to love rather than to a god. There was an image of a page from Isaac Newton's great work, the Principia Mathematica. There were photographs of cars, airplanes, trains, and rockets, fields of grain, schools, libraries, a supermarket. There was a photograph of Olympic sprinters racing on a track, chosen because it showed the musculature of the human leg, different races of humanity, and a form of both competition and entertainment, all in a single image. There was a photograph of a woman licking an ice cream cone, because it showed the human tongue and the act of tasting. The images were selected to give an alien civilization as complete a picture of life on Earth as possible, using the smallest number of photographs. After the images came the audio. The record contained spoken greetings in 55 languages, beginning with Akkadian, a language spoken in ancient Sumer about 6,000 years ago, and ending with Wu, a modern Chinese dialect. Each greeting was a simple message of goodwill. "Hello, from the children of planet Earth," said one. "Friends of space, how are you all?" said another. "Peace," said a third. Then came the sounds of Earth, a 12-minute montage that included the sound of surf, wind, thunder, birds singing, whales calling, dogs barking, babies crying, footsteps, heartbeats, laughter, and the roar of a rocket launch. There was the sound of a tractor, a horse and carriage, a train, a bus, a car, and a jet airplane. There was the sound of a kiss. The sounds were arranged to tell a story, a kind of audio journey through human civilization, from the natural world to the mechanical world, from the simple to the complex, from the sounds we share with animals to the sounds that only we can make. There was even a hidden message. The brainwaves and heartbeat of Anne Druyan were recorded for an hour and then compressed into a single minute. During the recording, Druyan had been meditating on the history of human civilization and her own feelings of love and wonder. If an alien civilization could ever decode those brainwaves, they would find a record of one human mind contemplating the universe. And then came the music, 90 minutes of it, 27 tracks chosen to represent the full breadth of human musical expression. The selection process was painstaking. Timothy Ferris, who served as producer of the record, consulted with musicologists, ethnographers, and collectors from around the world. The goal was not to include the most famous or popular music, but to capture the widest possible range of human musical creativity. Every track had to stand on its own as a work of beauty and complexity, something that an alien listener might find intriguing even without understanding the cultural context. There was Beethoven's Fifth Symphony, with its famous four-note opening, a piece of music so structurally elegant that some members of the team argued it would be comprehensible to any intelligent listener, human or otherwise. There was a Javanese gamelan composition called Kinds of Flowers, its interlocking metallic tones creating a shimmering wall of sound. There was a Senegalese percussion piece, driving and complex, built on rhythmic patterns that have been passed down through generations. There was a night chant of the Navajo people, ancient and haunting, a prayer sung under the stars of the American Southwest. Panpipes from Peru, performed by a musician from a tiny village in the Andes, whose name is not recorded, but whose music will travel through the galaxy for billions of years. A raga from India, with its slowly unfolding melodic structure and its deep connection to the time of day and the season of the year. Georgian choral music, with voices stacked in harmonies that are unlike anything in Western music. Bach, played on the harpsichord by Glenn Gould, precise and mathematical, and yet deeply emotional. The Rite of Spring by Stravinsky, wild and primal, a piece that caused a riot when it was first performed in Paris in 1913, and that now travels through interstellar space. Louis Armstrong singing melancholy blues, his trumpet warm and sad and unmistakably human. Chuck Berry's Johnny B. Good, a rock and roll song about a country boy who could play the guitar like ringing a bell, chosen because it captured the energy and optimism and sheer exuberance of mid-20th century America. The team had wanted to include the Beatles' song Here Comes the Sun, but the record company EMI would not give permission. One member of the team later remarked on the irony of a corporation denying humanity the chance to send one of its greatest songs into the cosmos over a question of royalties. There was also a printed message from President Jimmy Carter. It read, in part, "This is a present from a small distant world, a token of our sounds, our science, our images, our music, our thoughts, and our feelings. We are attempting to survive our time so we may live into yours." The record's protective cover was electroplated with a sample of ultra-pure uranium-238, an isotope with a half-life of about 4.5 billion years. By measuring how much of the uranium had decayed, a finder could determine how long the record had been traveling through space. Carl Sagan knew that the chances of either Voyager being found by an alien civilization were vanishingly small. The spacecraft are heading into empty space. Voyager 1 will not pass near another star for about 40,000 years, when it will come within about 1.6 light-years of a star called Gliese 445 in the constellation Camelopardalis. Even then, 1.6 light-years is an enormous distance. The golden records are, in all likelihood, messages that will never be read. But Sagan did not care about the odds. He said that the launching of this bottle into the cosmic ocean says something very hopeful about life on this planet. The records were not really for aliens. They were for us. They were a way of saying, this is who we are. This is what we sound like, what we look like, what we dream about, what we love. They were a declaration of existence, flung into the void with the hope that someone, somewhere, might hear it. And even if no one ever does, the act of sending the message was itself a statement of faith in the value of life and the possibility of connection. Today, both golden records are still traveling through interstellar space, protected by their aluminum jackets, carrying the sounds and images of a world that has changed enormously since 1977, but that would still be recognizable in those photographs and those songs. They are the most distant human artifacts in existence, and they will outlast everything we have ever built on Earth. The records are expected to remain playable for at least 1 billion years. Long after our cities have crumbled, long after our languages have been forgotten, long after the sun has expanded and swallowed the Earth, the golden records will still be drifting through the Milky Way, carrying the sound of Chuck Berry's guitar and a baby's first cry and the crash of waves on a beach that no longer exists. Let us return to the science, to what the Voyagers are finding now in the space between the stars. The interstellar medium is not the empty void that people often imagine. It is a thin but real substance, a gas made up of atoms and ions and electrons, threaded through with magnetic fields and bathed in cosmic radiation. Most of the atoms are hydrogen, the simplest and most abundant element in the universe. There are also traces of helium and heavier elements, the ashes of stars that have lived and died over the billions of years since the galaxy formed. The density of this gas varies from place to place, but on average, there is about 1 atom per cubic centimeter in the region near our Sun. That is incredibly thin, far thinner than any vacuum we can create in a laboratory. But it is not nothing. Over the vast distances between the stars, even this thin gas adds up, and it has properties, a temperature, a density, a magnetic field, a velocity that can be measured and studied. The Voyagers are our only direct observers of this medium. Everything else we know about the interstellar gas comes from indirect measurements, observations of how starlight is absorbed or scattered as it passes through the medium, or radio observations of the emissions from interstellar atoms. These indirect methods give us a general picture, but they cannot tell us about the detailed local properties of the medium. The Voyagers can. They are measuring the interstellar medium from the inside, particle by particle, field line by field line, vibration by vibration. And what they are finding is a medium that is more complex and more dynamic than anyone expected. One of the most important findings is about the shape of the heliosphere. For decades, scientists assumed that the heliosphere was roughly comet-shaped, with a rounded nose pointing in the direction of the sun's motion through the galaxy, and a long tail streaming behind, like the wake of a boat moving through water. This shape made intuitive sense. The sun is moving through the interstellar medium at about 15 miles per second, and the pressure of the oncoming gas should compress the front of the heliosphere while allowing the back to stretch out. But data from the Voyagers, combined with observations from other spacecraft like the Interstellar Boundary Explorer or IBEX and computer models, has complicated this picture considerably. Some models now suggest that the heliosphere might not have a long tail at all. Instead, it might be more like a sphere, or even a shape resembling a croissant, pushed and pulled by the magnetic fields and pressures of the interstellar medium. The direction and strength of the interstellar magnetic field play a crucial role in determining the heliosphere's shape, and the Voyager measurements of that field have been essential for constraining the models. Other models suggest that the heliosphere might have a shape more like a deflated beach ball, flattened in some directions and elongated in others, depending on the relative orientations of the solar magnetic field and the interstellar magnetic field. The exact shape of the heliosphere matters because it determines how well we are shielded from galactic cosmic rays, high-energy particles from outside the solar system that can damage living tissue and electronic equipment. The Voyagers have shown that the heliosphere is dynamic, constantly changing in response to the sun's activity. When the sun is active producing more solar wind, the heliosphere expands. When the sun is quiet, the heliosphere contracts. This was consistent with the fact that Voyager 1 and Voyager 2 crossed the heliopause at different distances from the sun, because the sun's activity level was different at the times of their crossings. The heliopause moves in and out, breathing with the sun's 11-year cycle, like a lung expanding and contracting. The magnetic field measurements from both Voyagers have also provided important clues. The finding that the magnetic field just outside the heliopause is parallel to the field inside was a genuine surprise. Before the Voyagers crossed, Scientists had expected the interstellar magnetic field to point in a different direction, since it should be shaped by the movement of the Sun through the galaxy and by the large-scale structure of the Milky Way's magnetic field. The alignment between the two fields suggests a more complex interaction at the boundary than anyone had imagined. It may be that the solar wind, as it flows outward and piles up at the heliopause, drags and compresses the magnetic field lines in a way that forces them into alignment with the interstellar field. Understanding this interaction is one of the key goals of the ongoing Voyager interstellar mission. The Voyagers have also shown that the heliosphere is not a perfect shield. Galactic cosmic rays, those high-energy particles from outside the solar system, do penetrate the heliosphere. Inside the heliosphere, the Sun's magnetic field and solar wind deflect many of these cosmic rays, reducing the amount of radiation that reaches the inner solar system. But the shielding is not complete, and the amount of cosmic ray exposure varies with the Sun's activity level. When the Sun is active, the shielding is stronger. When the Sun is quiet, more cosmic rays get through. Outside the heliosphere, in interstellar space, the cosmic ray intensity is significantly higher. Both Voyagers measured a sharp increase in cosmic rays as they crossed the heliopause. This has implications for future human exploration beyond the solar system. Any spacecraft or space habitat traveling outside the heliosphere would need much more robust radiation shielding than what is required for travel within the solar system. The cosmic ray environment in interstellar space is about twice as intense as what is experienced inside the heliosphere during solar minimum, and several times more intense than what is experienced during solar maximum, when the Sun's activity provides additional shielding. For astronauts on a hypothetical interstellar mission, this radiation would pose a serious health risk, increasing the likelihood of cancer and other radiation-related diseases. It is one of the many challenges that will need to be solved before humanity can seriously contemplate sending people beyond the heliosphere. In late 2023, Voyager 2's plasma wave instrument recorded multiple instances of density oscillations in the interstellar plasma, helping to map the characteristics of the interstellar medium. Each bit of data from the Voyagers is precious because it comes from a region where no other spacecraft has ever been or will be for many years to come. As Linda Spilker, the Voyager project scientist, has noted, every minute of every day, the Voyagers explore a region where no spacecraft has gone before. Every day could be the last. But that day could also bring another interstellar revelation. The team on Earth that operates the Voyager spacecraft is small but dedicated. Some of the engineers have been working on the mission for decades. They have watched the Voyagers fly past Jupiter and Saturn, Uranus and Neptune. They have guided them through the heliosheath and into interstellar space. They have solved problems that seemed unsolvable, sending commands across billions of miles of space to fix issues on spacecraft with 1970s era computers. They are, in a sense, time travelers, using technology from the disco era to do 21st century science. And they are also realists. They know the Voyagers will not last forever. The power is fading. The thrusters are clogging. The instruments are shutting down one by one. But there is a quiet beauty in this slow farewell. Voyager 1 is not dying. It is simply winding down, like a music box at the end of its song. Each instrument that goes silent takes with it one way of perceiving the universe. When the cosmic ray detector was shut down, Voyager 1 lost the ability to taste the high-energy particles raining in from distant supernova. When the low-energy charge particle instrument is turned off, it will lose another sense. But the magnetometer and the plasma wave subsystem remain, and they are enough. They can still hear the hum of the interstellar medium. They can still feel the direction and strength of the magnetic field. They can still tell us about the environment in the space between the stars. The last signal still carries meaning. With careful power management, engineers believe that at least one instrument on Voyager 1 could remain operational into the 2030s. That would give us more than 50 years of continuous data from the most extraordinary journey in the history of exploration. 50 years of signal. 50 years of conversation between a small machine and the world that made it. And even when the last instrument goes dark and the last radio signal fades to nothing, Voyager 1 itself will continue. It will keep moving through interstellar space, carried by its own momentum for millions of years. It will outlast every building, every road, every monument, every artifact that humanity has ever created. It will be among the last traces of our civilization, one small machine, drifting silently through the galaxy, carrying a golden record and the memory of a world that loved to explore. Let us think about where the Voyagers are going, not just in the next few years, but in the deep future, the kind of future that stretches so far ahead that it makes human history seem like the blink of an eye. Voyager 1 is currently heading in the direction of the constellation Camelopardalis, moving at about 38,000 miles per hour relative to the Sun. It is climbing steeply away from the plane of the planets, heading northward through the galaxy. In about 40,000 years, it will pass within 1.6 light-years of the star Gliese 445, a dim red dwarf that is currently about 17.6 light-years from Earth. By the time Voyager 1 arrives in its neighborhood, Gliese 445 will have moved closer to the Sun, making the encounter slightly nearer. But even at 1.6 light-years, Voyager 1 will not be close enough to be captured by the star's gravity. It will simply drift past, a silent visitor from a distant world. Voyager 2 is heading in a different direction, toward the constellation Sagittarius. In about 40,000 years, it will pass within about 1.7 light-years of the star Ross 248, another red dwarf. And in about 296,000 years, it will pass within 4.3 light-years of Sirius, the brightest star in our sky. These are the closest encounters the Voyagers will have with other stars for a very long time. None of these passages will bring the spacecraft close enough to any star's planetary system to be captured or deflected significantly. The Voyagers will simply drift through, like a leaf floating past a distant lighthouse, too far away to be affected by its light or its gravity. It is worth pausing to consider what these timescales mean. 40,000 years ago, modern humans were painting cave art in Europe and hunting mammoths on the steppes of Asia. Our entire recorded history, every empire and every civilization, every war and every discovery fits into the last 5,000 years or so. The Voyagers' journey to their first stellar encounter will take 8 times longer than all of recorded history. And that is just the first encounter. The journey through the galaxy will continue for billions of years. The timescales are so vast that they make human history seem like a single heartbeat in the life of the cosmos. After these relatively close passes, the Voyagers will continue to drift through the Milky Way galaxy. They will orbit the center of the galaxy just as the Sun does, completing a full orbit roughly every 225 million years. But they will be on slightly different orbits than the Sun, because the gravitational assist from Jupiter and the other planets change their trajectories. Over millions of years, they will gradually diverge from the Sun's path, wandering through different neighborhoods of the galaxy. The galaxy is mostly empty. The distances between stars are vast, and the Voyagers are small. The chance of either spacecraft colliding with a star, a planet, or even a large asteroid is essentially zero. They will drift in silence, untouched, for timescales that are difficult to imagine. In about 5 billion years, the Sun will exhaust its hydrogen fuel, swell into a red giant, and engulf the inner planets, including Earth. Mars may survive barely. The outer planets will be pushed to wider orbits. The red giant Sun will be hundreds of times larger than it is today, its bloated atmosphere extending past the orbit of Venus and perhaps even Earth. The planet we call home will be vaporized, its oceans boiled away long before the expanding Sun reaches it, its surface melted and absorbed into the dying star's outer layers. Everything that humanity has ever built on Earth will be gone. The pyramids, the cathedrals, the cities, the libraries, all of it. Eventually, the Sun will shed its outer layers and shrink into a white dwarf, a small, dense remnant about the size of Earth but with the mass of the Sun, that will slowly cool over trillions of years. The solar system, as we know it, will be gone, but the Voyagers will still be out there, still carrying their golden records, still bearing the images and sounds of a world that no longer exists. They will be among the last physical evidence that humanity ever lived, and they will continue to travel for billions of years, perhaps tens of billions of years, until the galaxy itself has changed beyond recognition, until the stars we see today have burned out and new ones have taken their places. The Voyagers will drift through a galaxy that looks nothing like the one they left, carrying a message from a civilization that existed for the briefest flicker of cosmic time, but that had the audacity to reach out and try to touch the infinite. There is a phrase hidden in the Sounds of Earth section of the Golden Record. It is encoded in Morse code, woven into the recording. The phrase is per aspera ad astra, through hardship to the stars. It was placed there as an inspirational message, a reminder that the journey to the stars is never easy, but always worth the effort. And there is another hidden message. The brainwaves and heartbeat of Anne Druyan, recorded in that single compressed minute, contain the electrical patterns of a mind in love. Druyan later wrote that during the recording session, she had meditated on the history of human civilization, and she had also thought about Carl Sagan and about the fact that they had recently declared their love for each other. She said that she hoped that some future civilization, billions of years from now, might be able to decode those brainwaves and find the story of two people who loved each other and who loved the idea of reaching out to the unknown. It is a beautiful thought, and it captures something essential about the Voyager mission. These spacecraft were built by scientists and engineers, people who deal in facts and measurements and data. But the mission itself was also an act of imagination, of hope, of love. It was a declaration that we are here, that we are curious, that we are not afraid of the dark, and the Voyagers carry that declaration farther than anything else we have ever made. As we approach the end of our journey tonight, let us return to the present, to February 2026. Voyager 1 is more than 15 billion miles from Earth. Its signal takes more than 22 hours to reach us. It is moving away from the Sun at 38,000 miles per hour. Its plasma wave instrument is still listening to the hum of interstellar space, still measuring the density of the plasma it passes through, still sending back data that no other instrument in history has ever collected. The signal is still there, faint but steady, the longest thread ever spun by human hands, stretching across billions of miles of emptiness, connecting us to a machine that left home nearly 50 years ago and never looked back. Its twin, Voyager 2, is about 12 billion miles from Earth, moving in a different direction. Its magnetometer and plasma wave subsystem are still operating too, still measuring the interstellar medium from a second vantage point. But it is Voyager 1 that holds the record. The farthest, the fastest, the loneliest, the first to leave the heliosphere, the first to hear the hum of interstellar space, and one day the first to fall silent. The Canberra antenna, the only antenna capable of sending commands to Voyager 1, is undergoing upgrades that will continue into early 2026. During this time, the Voyager team can receive data from the spacecraft, but cannot send new commands. Voyager 1 is on its own, running on autopilot, following the last set of instructions it was given. It is a reminder of how vulnerable this mission is, how dependent on the infrastructure here on Earth. And it is a reminder of how remarkable it is that Voyager 1 has survived this long. The engineers and scientists who work on the Voyager mission know that the end is coming. Not today, not tomorrow, but within the next decade. The power will drop below the level needed to operate any instrument. The last data will be received. The last signal will fade into the background noise of the cosmos, too weak to distinguish from the random crackle of the universe. And Voyager 1 will fall silent. It will be a quiet ending. There will be no explosion, no dramatic failure. The signal will simply grow weaker and weaker until the antennas on Earth can no longer pick it out from the noise. One day, the engineers will listen, and there will be nothing. Just the hiss of empty space where Voyager 1's voice used to be. And that will be that. The longest conversation in human history between a small machine and the world that made it will be over. But Voyager 1 will not stop. Voyager 1 will keep moving. It will keep carrying its golden record through the darkness. And somewhere, in the unimaginable future, when the sun is a cold, dark cinder and the Earth is a memory, one small spacecraft will still be drifting through the Milky Way, bearing the sounds of surf and bird song and Beethoven, and a baby's laugh and a mother's heartbeat, and the words hello from the children of planet Earth. Think about that as you close your eyes tonight. Think about those two small travelers, out there in the dark, farther from home than anything we have ever made. Think about the wall of heat they found at the edge of our solar system, and the gentle hum they hear in the space between the stars. Think about the storms of Jupiter and the rings of Saturn, and the geysers of Triton and the pale blue dot that is our home. Think about the golden record, spinning silently in its aluminum jacket, waiting for someone to find it, waiting for someone to hear the music and the greetings and the sounds of our world. And think about what it means that we sent them, that we, a species barely old enough to have invented writing, had the courage to launch two small machines into the void, not knowing what they would find, not knowing if anyone would ever hear their message, but doing it anyway, because we are curious, because we are brave, because we believe that the universe is worth exploring, even if we may never see the end of the journey. The Voyagers will outlast us. They will outlast our cities and our civilizations. They will outlast the Earth itself. And in some strange, beautiful way, that means that something of us, some echo of our curiosity and our courage and our love, will survive for as long as the galaxy endures. The Heliosphere, that great bubble of solar wind that shelters us from the harshest radiation of the galaxy, is always changing. As the sun orbits the center of the Milky Way, it moves through different regions of interstellar space, encountering clouds of gas and dust that can push the heliosphere inward, squeezing it smaller. At other times, the sun passes through relatively empty regions, and the heliosphere expands. The heliosphere we have today is shaped by the particular patch of interstellar medium we happen to be traveling through right now. 1,000,000 years ago, it might have been a different shape, a different size. 1,000,000 years from now, it will be different again. The Voyagers caught it at one moment in time, a snapshot of a boundary that has been evolving for billions of years. Scientists have compared the heliopause to a shoreline. On one side is the familiar ocean of the solar wind. On the other is the vast, uncharted sea of interstellar space. And just as a real shoreline is shaped by waves and tides and currents, the heliopause is shaped by the forces acting on it from both sides. The Sun's output varies over its 11-year cycle, causing the heliopause to move inward and outward. Coronal mass ejections, giant clouds of plasma blasted into space by solar eruptions, travel outward through the heliosphere and eventually slam into the heliopause, pushing it outward. And from the other side, the interstellar medium presses in, its own magnetic field and particle pressure competing with the solar wind for control of the boundary. The Voyagers are measuring these interactions in real time. Every bit of data they send back tells us something about the forces that shape the bubble we live in. And that information has real practical value. Galactic cosmic rays, those high-energy particles that originate in supernovae and other violent events in the galaxy, are a genuine hazard for astronauts and spacecraft. Understanding how the heliosphere shields us from these particles and how that shielding changes over time is essential for planning future long-duration space missions. There is also a deeper question. The heliosphere is not unique. Every star in the galaxy has one or something like one. The size and shape of each star's heliosphere depends on the strength of its stellar wind and the properties of the interstellar medium it is moving through. Some stars, particularly young, energetic ones, may have enormous heliospheres that extend for hundreds of astronomical units. Others, particularly old, quiet stars, may have small, weak heliospheres that barely extend beyond the star's immediate neighborhood. And some stars may have no detectable heliosphere at all, their weak winds overwhelmed by the pressure of the interstellar medium. By studying our own heliosphere with the Voyagers, we are learning principles that apply to heliospheres throughout the galaxy. We are learning how stars interact with the space between them, how the thin threads of gas and magnetism that fill the galaxy are woven together, and how the presence of a single star can create a pocket of relative calm in the otherwise turbulent medium of interstellar space. The interstellar medium itself is not uniform. It is filled with clouds of varying density, temperature, and composition. Some regions are hot and tenuous, heated by the shock waves from ancient supernovae. Others are cool and dense, the raw material from which new stars and planets will eventually form. The Sun is currently passing through what is called the local interstellar cloud, a warm, partially ionized cloud of gas that is about 30 light-years across. Before that, we may have been in a region called the local bubble, a cavity of very hot, very thin gas carved out by a series of supernovae that exploded in our neighborhood of the galaxy over the past few million years. The local bubble is a fascinating structure. It is a region of space about 1,000 light-years across, where the interstellar medium is extremely thin and hot, heated by the energy of perhaps 15 to 20 supernovae that have exploded in this part of the galaxy over the past 10 to 20 million years. These explosions swept the interstellar gas outward, clearing out the gas and leaving behind a hot, tenuous cavity. The Sun entered the local bubble sometime in the past few million years and is currently near its edge, moving through the local interstellar cloud, which itself is a small, denser region within the larger bubble. Understanding the structure of the interstellar medium near the Sun is important for several reasons. It affects the size and shape of the heliosphere, which in turn affects the amount of cosmic radiation that reaches the inner solar system. Some scientists have speculated that when the Sun passes through denser regions of the interstellar medium, the heliosphere could be compressed significantly, allowing more cosmic rays to reach Earth's surface. This could have effects on climate and on the evolution of life itself. These are speculative ideas, but they illustrate why Voyager 1's measurements of the local interstellar medium are so valuable. The Voyagers are giving us our first direct measurements of the local interstellar cloud. They are telling us what it is made of, how dense it is, how hot it is, and what its magnetic field looks like. These are measurements that cannot be made from Earth because we are inside the heliosphere, looking outward through the solar wind. The Voyagers are outside, looking at the interstellar medium from within it, without the filter of the heliosphere to distort the view. It is a perspective that we have never had before, and that we will not have again until another spacecraft follows the Voyagers into interstellar space. There are plans for such spacecraft. The Interstellar Probe, a concept being developed at Johns Hopkins University's Applied Physics Laboratory, would be designed to travel to at least 1,000 astronomical units from the Sun, far beyond the heliopause, carrying instruments specifically optimized for the interstellar environment. Unlike the Voyagers, which were designed to study planets and only later repurposed for interstellar exploration, the Interstellar Probe would use advanced propulsion to reach its target distance in 50 years. The mission is still in the concept stage, but it represents the next chapter in the story that Voyager 1 began. There are also more ambitious ideas. Projects like Breakthrough Starshot propose using laser-driven light sails to accelerate tiny probes to a significant fraction of the speed of light, fast enough to reach the nearest stars in decades. If these projects succeed, they will owe a debt to Voyager 1, which proved that interstellar space can be explored and that the interstellar medium is navigable. The night is growing deep now, and the stars outside your window, if you can see them, are the same stars that the Voyagers are sailing among. Not close to any of them, not yet, but among them, in the sense that the Voyagers have left the realm of the Sun and entered the realm of the galaxy. They are no longer solar system objects. They are galactic objects, citizens of the Milky Way in a way that we, bound to our planet and our star, can only dream of being. There is a quietness to this thought that feels right for the end of the evening. The Kaishi Voyagers are not rushing. They are not striving. They are simply moving steadily and patiently through a silence that has lasted for billions of years and will last for billions more. They carry no urgency, no anxiety, no deadline. They have all the time in the universe. And so, for the moment, do we? Consider the silence they are traveling through. It is not the silence of an empty room. It is not the silence of a forest at night. It is a silence more profound than anything on Earth. In the interstellar medium, the nearest atom might be a centimeter or more from its neighbors. Sound waves, which require a medium to travel through, cannot propagate in any meaningful way. The plasma hum that Voyager detects is not sound in the way we experience it. It is an electrical vibration, a fluctuation in the density of charged particles, translated by the spacecraft's instruments into frequencies we can hear. The actual experience of being out there, if a human could somehow survive it, would be one of absolute total unbroken silence. No wind, no waves, No birdsong, no traffic, no voices. Nothing but the beating of your own heart and the whisper of your own breathing, the last sounds in a universe of stillness. And yet that silence is not empty. It is full of energy, of cosmic rays streaming past at nearly the speed of light, of magnetic field lines stretching for light years, of the faint glow of the cosmic microwave background, the afterglow of the Big Bang itself, still shining weakly in every direction, the oldest light in the universe. The Voyagers are bathed in this ancient light, though they cannot see it. Their cameras are off. They can only feel the particles and the fields, the invisible architecture of the space they travel through. The discoveries that the Voyagers have made, the volcanoes of Io and the ice of Europa, and the rings of Saturn and the geysers of Triton, and the wall of fire at the edge of the solar system and the hum of interstellar space. These are gifts. They are knowledge freely given, offered by two small machines that have asked for nothing in return. They have not complained about the cold or the loneliness or the slowly fading power. They have simply done their job, day after day, year after year, decade after decade, sending their whispers home across the dark. And we have listened. We have built the antennas and trained them on the sky and decoded the faint signals and turned them into maps and charts and images and understanding. We have taken the raw data and woven it into stories, into knowledge, into a picture of our corner of the galaxy that is richer and more detailed than anything our ancestors could have imagined. That is the legacy of the Voyager missions. Not just the data, not just the discoveries, but the act itself. The act of reaching out, the act of saying, we want to know, we want to understand, we want to see what is out there beyond the edge of what we know, and we are willing to spend decades and billions of dollars and the best years of our brightest minds to find out. The space between the stars is not empty. The Voyagers have shown us that. It is filled with plasma and magnetic fields and cosmic rays and the faint hum of matter vibrating at the edge of perception. It is a place of extremes, where temperatures reach tens of thousands of degrees, but there is not enough matter to warm your hand. It is a place where the sun's influence fades to nothing and the wider galaxy takes over. It is a place that is both utterly alien and strangely familiar, because it is made of the same atoms, the same forces, the same physics that govern everything on Earth. We are part of this medium. The atoms in our bodies were forged in the hearts of stars that exploded billions of years ago, scattering their remains across the interstellar medium. Those remains were gathered up by gravity, compressed into a new star, our Sun, and the planets that orbit it. And now, some of those atoms have been shaped into machines that have been sent back out into the medium from which they came, to measure it, to taste it, to listen to it. There is a circularity to this that is deeply satisfying. The universe created us. We created the Voyagers. The Voyagers went out into the universe and sent back what they found. And what they found was a universe that is wilder, stranger, more beautiful, and more full of surprises than we ever imagined. So let the Voyagers sail on. Let them carry their golden records through the dark. Let them measure the hum of the interstellar medium and the whisper of the galactic magnetic field. Let them be our ambassadors to the cosmos, our message in a bottle, our love letter to the universe. And as you drift off to sleep, carried by the gentle rhythm of these words, imagine yourself out there with them. Imagine the silence. Imagine the darkness, broken only by the cold, distant light of a billion stars. Imagine the faint crackle of cosmic rays, and the soft hum of plasma vibrating in the void. Imagine the golden record gleaming in the starlight, carrying the sounds of home to a place where no one may ever hear them. It is peaceful out there. Cold, yes. Dark, yes. But peaceful. And somewhere in that peace, two small spacecraft are still moving forward, still exploring, still carrying a piece of us into the unknown. The solar wind is behind them now. The sun is just another star, and ahead of them, stretching out in every direction, is the galaxy. 100 billion stars, trillions of worlds, and the silence of the deepest, longest night you can imagine. Good night, explorer. The Voyagers are out there, keeping watch. They have been traveling since before many of us were born, and they will continue traveling long after we are gone. But right now, in this quiet moment, they are ours. They belong to everyone who has ever looked up at the night sky and wondered what was out there. They belong to everyone who has ever felt small under the stars and been comforted by the thought that our curiosity makes us larger than we seem. Sleep well. The cosmos is vast, but it is not empty. And somewhere out there, moving at 38,000 miles per hour, through the gentlest rain of plasma, a golden record is playing. It is playing the sounds of Earth, the crash of waves, the song of a whale, the laugh of a child, the note of a trumpet, and the steady, quiet heartbeat of a woman who was thinking about love and the stars, both at the same time. That is what Voyager found at the edge of our solar system. Not just a wall of fire, not just a boundary between the known and the unknown, but a reminder that the universe is full of things we have not yet discovered, and that the best way to find them is to keep moving forward, into the dark, with our eyes open and our hearts unafraid. The probes drift on. The hum continues. The stars are waiting. And so, gently, peacefully, we close our eyes. Let the Voyagers carry us into dreams, dreams of distant worlds and ancient storms and frozen geysers, and the thin, bright line of a ring around a gas giant. Dreams of the color blue, seen from 1 billion miles away, a tiny dot of home in the endless dark. Dreams of a record spinning in silence, its grooves full of music that no one has heard yet, waiting for a listener who may never come, but was worth sending to anyway. Because that is what we do. We reach out, we send messages, we fling bottles into the cosmic ocean, and we hope. The Voyagers taught us that the edge of the solar system is not the end of anything. It is a beginning, a doorway, a place where one kind of space ends and another kind begins. And on the other side of that door, there is a universe so large and so old and so full of wonders that even two spacecraft traveling for 1 billion years could not explore more than the tiniest fraction of it. And yet we sent them, and they went, and they are still going. And that, more than any discovery, more than any photograph, more than any measurement, is the most remarkable thing about the Voyager mission. We did it, we built them, and we launched them, and we listened, and we learned. And when their lights go out, and their signals fade, and they become silent wanderers in the dark, they will still carry the proof that once, on a small blue planet orbiting an ordinary star in the arm of a spiral galaxy, there lived a species that wanted to know. That is enough. That is more than enough. That is everything. Rest now. The Voyagers will keep going. They always have. They always will. Per aspera ad astra. Through hardship to the stars. Good night. The stars are not going anywhere. They will be there when you wake. And so will the Voyagers. A little farther from home than they were when you closed your eyes. A little deeper into the great silence of the galaxy. Still carrying their cargo of human hope and human music and human love through the longest night there is. out past the heliopause, where the solar wind dies and the interstellar medium begins. The temperature is astonishing, but the touch is gentle. The few particles per cubic centimeter drift like motes of dust in a cathedral, each one moving at tremendous speed, but so far apart from its neighbors that the space between them is emptier than the best vacuum we have ever created in a laboratory on Earth. This is the medium through which the Voyagers travel. This is the ocean they are crossing, and it stretches for light years in every direction, all the way to the next star, and the next, without end. In this ocean, the Voyagers are smaller than a grain of sand in the Pacific, but they carry something that the ocean does not have. They carry meaning. They carry the knowledge that someone cared enough to send them, that someone wanted to know what was out there, that someone believed the journey was worth taking, even if the destination could never be reached. And that is perhaps the most beautiful thing about the Voyager mission. Not the volcanoes of Io, or the rings of Saturn, or the geysers of Triton, or the wall of fire at the edge of the solar system. All of those are magnificent, but the most beautiful thing is simpler than all of them. It is the fact that we tried, that we reached out into the dark with nothing but our curiosity and our courage, and that we found a universe that was grander and more surprising and more full of wonder than we had dared to imagine. The hum of the interstellar medium is still there, faint and steady, a single note playing in the void, and the Voyagers are still listening. And somewhere, in a control room in California, a handful of dedicated engineers are still receiving the signals, still decoding the data, still adding to the story that began nearly 50 years ago with 2 rockets lifting off from a beach in Florida. It is a story that will not end when the Voyagers go silent. It will not end when the last engineer retires. It will not end when the data archives are finally closed. Because the story of the Voyagers is not just about 2 spacecraft. It is about us, about what we are capable of when we aim for something beyond ourselves, about the light that curiosity brings into the darkness. And now, truly, it is time to rest. The universe will wait. It has been waiting for billions of years. It can wait a few more hours while you sleep. And when you wake, the Voyagers will still be out there, faithful and tireless, measuring the hum of the cosmos and carrying our golden message through the stars. Sleep now. Dream of distant worlds. Dream of rings of ice and moons of fire and a pale blue dot floating in a sunbeam. Dream of a golden record spinning in the dark, playing music that no one may ever hear, but that was worth recording anyway. The Voyagers are with you. They have always been with you. They belong to everyone who has ever wondered, everyone who has ever dreamed, everyone who has ever looked up at the night sky and felt both small and infinite at the same time. Good night, explorer. The stars are singing, and the Voyagers are listening, and so, in your own quiet way, are you. The night settles in, the world grows still, and out there, in the great and gentle dark, 2 small spacecraft continue their voyage. They have seen more than any traveler in history. They have touched the face of every giant planet, felt the heat of volcanic moons, tasted the thin plasma of interstellar space. And now they drift, patient and purposeful, carrying their cargo of human dreams through an ocean of stars that stretches beyond imagining. They will be there tomorrow. They will be there next year. They will be there long after the memory of this night has faded. 2 golden records, 2 aging computers, 2 sets of instruments slowly winding down, sending their last signals home, and then silence, but not emptiness, never emptiness, because even in silence, the Voyagers will carry the proof that we existed, that we wondered, that we reached out with our small hands toward the infinite and said, "We are here, and that is enough. That is everything." That is the story of Voyager, 2 spacecraft, 48 years, 4 planets, dozens of moons, rings of ice and dust, volcanoes of sulfur, oceans hidden beneath frozen shells, geysers of nitrogen erupting on the coldest moon in the solar system, a wall of fire at the edge of the sun's domain, a gentle hum in the space between the stars, and a golden record spinning in silence, carrying the sounds of a world that loved music and laughter and the crash of waves on a shore. That is what we sent into the dark. That is what we gave to the cosmos. And it will travel on through the longest night imaginable, long after we are gone, bearing witness to the fact that once, on a tiny blue world, a curious species looked up at the stars and decided to go.